morning. I'm Jonathan Shahad,
I'm Janatip Sintanwan.
and today we're going to present to you our AJ CPU. So today on our agenda, first off, we're going to tell you about the AJ CPU. We're going to tell you a little bit about the memory architecture and its organization. We'll tell you about its advantages over the standard vanilla MIPS CPU. And lastly, AIM will tell you about some of our enhancements that we have incorporated. So the AJ CPU is based on the MIPS ISA. It's been expanded with 8051 instructions. This allows our processor to become more programmer friendly, giving us some of these expanded instructions. It's based on a 32-bit load store architecture. Has 45 total instructions. 33 are from our MIPS baseline, and we have added 12 expanded instructions. And we have also added implemented stack operations. And side note, this is the actual layout of the MIPS CPU on the die, so if you're curious about that. So here's a simplified top level, and as you can see, the instruction memory is actually contained inside the CPU, but this is just showing you the sizes. So we have a 4K instruction memory, 4K data memory, and a 1K I/O memory. And these are for simulation. They're not actual, like, it's 32-bit, so it's addressable up to 4 gigs, I suppose. Yeah, so some of our registers, there's 32 registers. Each one is 32 bits wide. Some important registers, we have the 0 register. This has a 32-bit 0. We have the S and T registers are used for our operands in our instructions. A0 through 3 are arguments for function calls and function arguments. And then we have our stack pointer and our return address. Stack pointer is important because this is also incorporated into our stack operations. So here's our IDP. As you can see, everything in gray is our instruction data pad, and here we have our instruction unit. This mux out here is our PC mux. It allows us to choose what we want to load our PC input with. So depending if we want to branch or jump, or if we want to send our resultant of our ALU. So this will be sent into our instruction unit and our IR register. So we have a mux on our D address. This can be selected from either our D address, T address, our return address, or our stack pointer. So this allows us to do stack operations. And then we have a S address and a stack pointer into our S address as well. Our Tmux will take our output from our register file, and it can handle that, or it can take our sign extension 16-bit. This is used for immediate, our program counter, or we also need this PC and flags for our stack operations to push them onto the stack so we don't lose their contents. And then you can see our barrel shifter is independent from our ALU, and I'll explain a little bit more about that. So there's actually a function select that's for our ALU that's not shown. And we have 4 registers going to our YMUX. This allows us different height or low depending on if we have multiplication divide, our ALU output, and DN comes from our memory I/O. And I'll explain more about that in a couple slides. So here's an overview of our flags. So we have our MIPS ALU, or our ALU as a whole right here, with our multiplier and our divider. So our ALU pushes out our resultants, and we have a multiplier that has a 64-bit product that's loaded into our high and low registers, and we have a divider that has a 64-bit resultant, and that has our remainder in the upper 32 bits and quotient below with 32 bits. Our carry and overflow flags are generated by our ALU. Our 0 flag is generated if our resultant is 0, and our negative flag is set high if our 31st bit of our low or high register are 1. So memory architecture is based on a big endian format. They are byte addressable, 32-bit of address space. Each instruction contains 4 1-byte location, 8 bits for each word or each location. So PC is incremented by 4 each time, and our memory is simulated to be 4K. So you can see here is a sample of our memory loading. So it's big Indian format, therefore our LSB is sent to our highest order, and our MSB is sent to our lowest order, as you can see right here. And all of this consumes 1 instruction. So here we will show you our barrel shifter. Allows for shifting up to 32 bits in 1 clock cycle. The shift amount over here specifies how many bits we would like to shift, and it operates in parallel to the ALU, so they're independent of each other, depending on the function and our select from our YMUX over here. So you can see the path goes from our register file from RT into our barrel shifter, into our YMUX, and out. And we have 3 main instruction or baseline instruction formats: the R-type, I-type, J-type. Opcode specifies which instruction, and if it's R-type, we may have a function. This will specify furthermore which instruction type. So J-type is used for jumps, I-types are used for immediates, and R-types are used for mostly arithmetic and logical operations.
How come the opcodes say 0 all the time? That's not correct for I-type, is it?
Right, it's just a placeholder.
Okay.
Yes. And our E-type enhanced always begin with the 1F E key. This is to make it MIPS compatible, so we don't overwrite any of the other opcodes. And our function actually specifies which enhanced instruction we are talking about. And AIM will present to you our enhancements.
Alright, so after we overview the all MIPS architecture, so we're going to begin with the data path of our enhancements for each instructions. The first one we're going to do is branch greater than or equals, or BGE. For after we fetch and decode instructions, and we're going to get the data from from S field of the instruction into RS, and the same way we get into RT. For the first class of the BGE instructions, we're gonna do subtract RS and RT in ALU and see if we're gonna get the negative flags. If it set the negative flags, which means RS and RT are even, and then if it's not set the negative flags, and the previous is zeros. If it's not set the negative flags, which means RS is greater than RT, we will load the PC and will be branched to the new address. And then the second instructions is the branch less than. It's similar to the previous one. We subtract RS and RT in LLU, and then we see the flags. If the zero flag is, if the negative flag is set, meaning that the RS is less than RT, then we branch to the new address.
So are these signed or unsigned branches?
So this one is unsigned.
Unsigned branches.
For the next instructions, we have clear. So clear is pretty simple. In our instruction, we define after 1F, we define that R0 plus R0 to ALU out, and on the next clock we write back the ALU out into register file within the RT address. Any questions so far?
Why would we need a clear if I could just do subtract a register from a register and put it in the same register?
So it's basically it just use 1 clock for these instructions after decoding.
So it saves the clock?
Yeah.
Okay.
So for the next one, we do have something we kind of proud to present is document jump not equal to 0. So we basically, the idea is, so okay, here, so we have, yeah. So we do RS and put it into LAU out, recommended by 1, and put it into our LAU out, and then see if it's flagged. If it's flagged, we're gonna if it's not if it's not 0, if that RS or the loop counter or whatever, if it's not 0, we're gonna branch into some address. And in meanwhile, we're gonna save that recommended number into the register file in the same place that we have.
So you're not testing the 0 flag that's registered, you're testing the flag from the ALU.
Yes.
So why have a 0 flag?
So if it's 0 flags, meaning that the loop counter that we pass into our RS or RT field is equal to 0, and then we flags.
Yeah, I love the instruction, but why do we have a 0 flag if you're not going to test the 0 flag? You're going to test the status combinational output from the ALU.
It's just a different way to test it. I mean, yeah, we can test the 0 flag, but we would be accessing the flag register. If we have the operations like right in front of us, might as well just check the resultant. So it's just a different way to check.
Okay.
So on the next one, we do move from RS to RT. So basically, we pass RS into LAU out, and then we put the LAU out back into the RT address, and it register file on RT field. And then go to the next. So the next one is no operations, which is NOP. So we load from the LAU out, from this state, we just passing the LAU out back into LAU and put into LAU out. It's a similar, it just one clock, so it set the state, then add immediate of 0 into itself. Something.
And the reason we actually implemented the no-op is we were going to attempt pipelining another time, so we knew we would need the no-op.
Alright, for the next one, we do have pop and push. All pop is going to be post increment. Post increment is mean we read the data from data memory, and then we increment the stack pointer address, and then we put it back into register file. So the first step, we wrote the stack pointer address from the register file, and then put into RS. For the next clock, we're going to parse the RS into LAU out, so the stack pointer is ready to use. And after that, we send stack pointer address into the data memory, and then so we can chip select the data memory and read the data, put it into data in, and now we're gonna pass the stack pointer address for 1 clock, and after that, for the last clock of the pop instructions. For the last clock of pop instructions, we are gonna send the stack pointer address into the data end. And then for the push, we're gonna push the data from RT field into the data memory. And meanwhile, we're gonna decrement the stack pointer, and after that, we're gonna store the stack pointer address back into the register. So yeah, the first clock, we load the stack pointer into RS, and then RS, we parse the RS to LAU out, so it's be ready, the address is be ready. For the next clock,
But you subtracted on that clock, right?
we subtract on this clock when we do send the data out to the memory, and then we send the stack pointer back into LAU and put decrement by 4, then put it back into LAU. So it's we be ready to store it back on the next clock, right here.
Okay.
Is there any questions?
So the first clock you load RS. Next clock, out ALU gets RS minus 4.
No,
Because
it
that
just-
would be
just pass.
that's a pre-decrement. You decrement first.
Oh
and
yeah.
then
It's
that's your
pre-decrement.
address.
Sorry about that. Yeah, it's pre-decrement first, and then we just push into the data memory, and then we just pass one clock, and then we just store back.
What clock did RT get loaded with the thing you're going to write?
But after we recommend the pointer, and then we just push out RT into data memory.
Okay, yeah, that makes sense.
Into our last but not least, this is the rotate left and rotate right. Rotate left and rotate right have the same data path. So basically, we just use the data from RT, put it into barrel shifter, into the end. So we will have the chips amount and chip select, which is showing that how many bits that you want to chip, and what kind of shifting that you like, either rotate left or rotate right with that shift amount. And before that, we put into LRU and then put it to register file. And after all the work, we have to redefine as a we have to modify. This is like a snake code from our instruction memory. So the things that we do is like we load from R1, R2, R3 with some numbers, and then we push 1, push 2, push 3. So it's going to show up here. We have all register right here, 1, 2, 3. And then we're going to have another one that show that we have data on the stacks. So after we push 3 of them, it's going to show up here by in order. This is the first order, second order, and third order. And then we do one instruction for no off, just to test if it work. And then after that, we pop to R4, pop to R5, pop to R6. So it's going to come back in order like that. So as you can see, we pop R4 first. So we get ABC, which is on the top of the stack at the moment. And then we get this and that. And after that, we're going to do branch less than, comparing R1 and R2, which is this and this. Since it's all branch less than is unsigned, branch less than is unsigned, so we're going to branch to BLTP when we go doing this. At here, we load R16 with all ones, meaning that we pass the test. And then we do branch, we compare again, we do branch greater than. So compare R6, which is the positive number, compare with the zeros. So it should branch into VGE pass without doing this.
What's R6? I don't know, when did R6 get loaded?
You go back one slide. So R6
From the previous?
Yeah.
Okay.
It's 1, 2, 3, 4.
Yeah.
Alright, so after that, I moved R16, which was the 1111 into 17. So we will get the result right here. And as you can see, we passed the two tests, right? Then we're gonna do the next instruction, which is rotate left and rotate right. We have to rotate the R17 by 2 to the left. We will get 4, 4, 4, 4. And then we rotate right by 3 amount. We will get 2, 2, 2, 2. And after that, we kind of set the loops for the next instructions. So right here we have a counter on R13 and R14, which we get we put 7 into R13 and 14, and then we load number 9. I mean register 9 as a 0001 to be a pattern that we want the walking ones to left and right, and then we set the R15 as a memory address. So as you can see right here, 7 and 9, 15. Alright, and on the large page we have 2 loops right here. First loop is to write in on I/O, and we're gonna do walking 1 to the left, because so we once we enter here, we save the 001 into the I/O, and then we shift left by 4, so we'll get walking 1 to the left until it here recommend jump not 0. Obviously that R13 the first time is 7. We're gonna recommend it by 1, and it's not 0. It's gonna jump back to the top of this loop, and then do it again. We will get walking 1 to the left. And then, as you can see here, after we finish the loop, the R13 will be 0, and then have walking 1 on the left. And the memory pointer will be 0DC. And then after that, we do move R9, which is this guy right here, into R10, so we can operate for the next loop. And then the next loop, we do the same thing, but we do shift right logic by 4, so we get walking
Mhm.
one to the right, right here. So now our counter will become 0, and then R10 becomes 0, 0, 1, just like the beginnings. And then we do the same thing, document jump not 0 if it's not 0, obviously. R14 become, if it's not 0, it's going to do again and again, and now it's 0. So after we finish all the instructions, so we're going to clear the register 1 just to verify that we finished all the instructions. Alright, here's just the result. So you can see that R1 is 0, meaning that we passed all the instructions, all the tests. And R2, R3 is what we initialized, and R4, 5, 6 is what we popped out. And then R7 and 8 is a result from 7 and 8 is a result from rotate left and rotate right. And R9 and R10 is the result from the loop, on a memory loop. And then R13 and R14 is all loop counter, R15 is the last memory pointer, R16, 17 is pass flags. Can you go to that one? So as you can see, as all data memory and I/O memory we have walking 1 to the left, and data memory have walking 1 to the right. And that's it. Do you have any questions?
No time. Thank you very much.